Okay, good evening, everybody. Well, I'm saying evening because it's evening for me. Good morning or good afternoon, whatever time of the day it is when you're watching this video. I hope that everybody had a successful day yesterday and you were productive and you were able to find all of the resources to get your work done. Just a couple of notes. Some of you have told me that my YouTube videos have missing audio in the right channel, and I think I've fixed that problem. So in the future, you will have audio from both speakers if you're listening in stereo. And there's another issue I want to talk briefly about here. Whenever you are looking at viewing those PDF files or printing PDF files that originate within that shared folder, it's always a good idea to download them to your computer and open them with a PDF program like Adobe Acrobat, or there's a program called Foxit PDF Reader. If you double click on the file in Google Chrome, Chrome attempts to open the PDF and it doesn't do a very good job, so sometimes things get a little jumbled and sometimes things are missing. Just make sure you download it first. Today we're going to be looking at finding maxima and minima. The word maxima is just the plural of maximum. So rather than saying maximums, we say maxima. And the same goes with minima. Minima is the plural of minimum. This is on page 2 of your handout. We're going to be spending at least 2 days on this. I want to go through some things that we already know. We should know this. The first point is that when we're talking about a function increasing or decreasing, I actually want to make another point here that I don't have typed up. When we talk about function, when I use that word function, I am talking about f of x, but f of x is y. So whenever we talk about a function increasing, we're referring to the y coordinate increasing. The more broad point, though, the important point, is that a function is increasing or decreasing if y increases or decreases as we go from left to right. That's kind of the way we always look at things, from left to right. Now, the 2 points below are fairly basic. If you have a function that is decreasing from left to right, then it must have a negative slope. And if you have a function that's increasing from left to right, it must have a positive slope. And since slope is defined by the derivative, when the derivative is negative, the slope is negative and the function is decreasing. If the derivative is positive, the slope is positive and the function is increasing. So if I were to take a look at this function, f of x is of course plotted on the vertical axis and there's x, and I look at this function, it's a very boring function, and I asked you about this point right here, which I'm going to call point I. The function is increasing at that point because the slope is positive, and if the slope is positive, the derivative is positive. In case it's lost on you, I use the letter I because the function is increasing. If I were to take a look at this point here, and I'm going to label it as D, at that point on the function, there's a negative slope, which means the function is decreasing from left to right, and that means the derivative is negative. So, bottom line, and I'll just do this here so I don't crowd things out. If you had a graph that looks like this, then you're talking about a region over here where dy dx is greater than 0. You're talking about a region to the left where dy dx is greater than 0, but over here on this side, you're talking about a region where dy dx, the derivative is less than 0. Of course, there's some point here where the function does not have a positive slope and it does not have a negative slope, but it has a slope that happens to be equal to 0, and that's going to be a point of interest because that's a maximum value. There are some other things that are new. There are different types of maxima and there are different types of minima. There is an absolute maximum, which is the highest value of the function anywhere the function is defined. But there are also local maxima, which are points. I just want to highlight this so that you're following me here. there are absolute maximum, and those points, an absolute maximum is a point where it's the highest value of y at that location everywhere, but there are also what we call local maxima, and that would be a point where if you look in the vicinity, if you look in that region, in that locality, it's a maximum. But it's not necessarily the biggest maximum there is. There could be bigger maximums. And the same goes with minima. An absolute minimum is the lowest value of the function everywhere. A local minimum is the lowest value of the function in a particular region of the function. We have some other things that we have to define, and you might have to go back and read this or pause the video and think about it, but we have these things called critical points. And if the derivative of the function, dy dx, if the derivative of the function is equal to 0, or if the derivative of the function is undefined, then that x coordinate is referred to as a critical number. And then the point that the first example is going to hopefully drive home is that all maxima and minima exist at critical values of x. So let's just go slow with this because this is tricky. If you identify a point that is a maximum, then that point must correspond to a critical value. Always. If you identify a point as being a minimum, and whether it's global, I'm using the word global to mean absolute. Whether the minimum or maximum is absolute or local doesn't change the fact that every maximum occurs at a critical value of x, and every minimum occurs at a critical value of x. But not all critical values of x correspond to maxima. So you have all these critical values of x, and some of them correspond to maxima, but not all of them. Some of them correspond to minima, but not all of them. So I'm using an analogy here. All maxima and minima are at critical values of x, but not all critical values of x correspond to maxima or minima, is equivalent to me saying all chickens are birds. But not all birds are chickens. Chickens are a subset of all birds, and maxima and minima are a subset of critical values of x. So there's a procedure we're going to use to find maxima and minima, and we'll get to that in example 2. But let's take a look at example 1 first. I've created this overly ambitious graph, and I think I might have been overly ambitious. It's pretty complicated. It's got a couple of asymptotes, and it has all of these kind of weird shapes and these corners. Please don't circle anything yet. I'm just pointing something out to you, that these points right here have something in common with each other. And the thing they have common with each other is even though the function exists at those points, the derivative does not. And I might as well attempt to explain this and get this out of the way right now. The derivative does not exist at those points because the derivative of a function, and again, this is just me talking, there's no need to write this down, is originally defined as a limit. I'm not going to write down this part. It's unimportant for my discussion with you right now. The derivative is a limit, and there is something we learned in chapter 1 about limits, and if you could go back and play back that lesson, you would have heard me say in the lesson, look, there's only one reason we're looking at left and right hand limits. At the time, we learned that the limit only exists if the left and the right hand limits are equal. The only reason we learned that is so that I can use that here to explain that the derivative is not defined at these points. It's not defined at these points because the left-hand slope and the right-hand slope are not approaching the same value. So the left-hand limit and the right-hand limit are not going to be equal, so the derivative doesn't exist. It gets even more obvious at these other 2 points that are still circled because there is a left-handed limit here the slope is approaching some number, but there isn't even a right-handed limit. So those points are points where the derivative is not defined. Now let's jump ahead to the question, because the first part of the question says, identify the critical values of x by circling the point or labeling x critical on the x-axis. Okay, and I've got circling highlighted because I believe it says circle on your handout. Okay, so what are critical points? Critical points are where the derivative is undefined or equal to 0. So we can start by circling these points. Those are all critical points. They occur at critical values of x because the derivative is not defined there. Now, the other critical points, there's actually one more critical point here where the derivative is undefined, and it's right here. And the derivative is undefined there because the slope is vertical at that point, which means the slope is infinite, and we don't define infinity. We also have this point, this point, this point, and this point, and this point, and this point being critical because, and I don't know how you want to communicate this to yourself, but the ones that I'm circling in green are places where the derivative is equal to 0. The ones that I've circled in red are where the derivative is undefined. So those are all of the critical values of x, except for one. There is a critical value of x right here. And that's why, if you read the question carefully, what I have said is circle the point or label it on the x-axis. Because there is one critical point, whatever this x-coordinate of that vertical asymptote is, there's one critical point that's not actually a point on the graph. So the ones that are circled in red are critical because the derivative is undefined. The ones that are circled in green are critical because the derivative is 0. This point right here that I'm indicating is critical because the derivative is not defined there because the function doesn't exist there. So you have, if I count them left to right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 critical points here. The second part of the question is to identify the max-mins. So I'm going to use the letter L to represent local. This is a local max. And the reason it's not an absolute max is because this part of the function over by the asymptote goes up forever. So in fact, this function won't have a maximum. Do we have any other local max? Well, we have a local max here, a local max here, a local max at this point. I don't think there are any more. We have a local min here, a local min here. This point is an absolute minimum because there's no point anywhere else on this function lower than that. This is a local min, and this is a local min. And just to round this off, remember, you can pause the video if you like. What you can see is that every single maximum or minimum corresponds to a critical value of x, but there are critical values of x here, here, here. There are three, I count 1, 2, 3 critical values of x that are not max-mins. So all max-mins occur at critical values of x, but not all critical values of x give you max-mins. That's the lesson to be learned here. Now let's take a look at the actual math here. Example 2 says, let's algebraically find maxima and minima for a variety of functions. And the first function is very simple. This is a quadratic function. So the first step, if we want to find out, everybody, where the derivative is greater than 0 and where the derivative is less than 0, then I guess we'd better worry about where the derivative equals 0, and that means we have to find the derivative. I'm going to go with the dy dx notation. The derivative is negative 5 minus 14x. I hope you haven't forgotten how to determine derivatives. Looks okay. So what we're going to do is we're going to write that derivative in factored form. I'm going to take a negative 1 out and write 14x plus 5. So I'm just checking my work here. The derivative is negative 5 minus 14x. I'm taking a negative out. This is just what I would prefer to do. You don't need to take it out, but I like that. Because I can then look and see that the critical numbers are negative 5 over 14. In fact, that's it. That's the only critical number. And just make a note to yourself that today, all of your critical numbers will be the ones where the derivative equals 0. You're not going to encounter derivatives being undefined until a little bit later in the course. So now what we're going to do is something that we've already done with motion problems. We're going to make a derivative chart. I'm going to break up the domain that goes from negative infinity up to infinity into a domain that goes from negative infinity to negative 5/4 and from negative 5/4 to positive infinity. So I'm taking the domain of all real numbers, which is the domain that this function exists over. It's a polynomial function. And I'm slicing it at the critical value of x. On the top, I'm going to put the factors of the derivative. And the factors of the derivative multiply to give the derivative. And now we're going to complete this table by saying that negative 1 is negative in either of these regions. And then we have to figure out whether 14x plus 5 is positive or negative in this interval. So we can go ahead and put in a value for x, but what you're going to discover is it's negative and then it's positive. When I multiply the two factors, this negative by this negative, it gives me a positive. When I multiply these two factors, I get a negative. So we're done, almost. What does this tell us? It tells us that in this interval, in interval A, I'll call it, the function is increasing because the slope is positive because the derivative is positive. And in interval B, the function is decreasing. And that means that if it increases before negative 5 over 4 and it decreases after negative 5 over 4, that there must be a maximum at negative 5 over 4. And for the sake of brevity, which means I want to keep this shorter if at all possible, you do, of course, have to find the y coordinate to identify the location of the max. I'll leave that to you. You would take negative 5 over 4 and put it into the original function to find the maximum value. Again, all of these ones you're doing today are polynomials, so they are defined everywhere. It will be smooth everywhere. There will not be any undefined points for the derivative. Let's do this again. S prime of t, I'll use this notation this time, is 3t squared minus 24t plus 36. That looks okay. I want to always express my derivative in factored form. It finally makes sense why I've been harping on you for the first 5 weeks of classes that you have to factor things completely. So I take a 3 out of everything, and then I can factor that quadratic into t minus 6, t minus 2, which means the critical values that make the derivative 0 are 2 and 6. So now I construct a first derivative table. My first derivative table is going to have an interval from negative 6 up to 2, from 2 up to 6. I apologize, I'm tired, I guess. I just said from negative 6 to 2. I meant to say from negative infinity to 2, then from 2 to 6, then from 6 to infinity. Notice that if you have two critical values of x, you get three intervals. Across the top, I'm going to put the factors of the derivative. I guess we don't really need to put the 3 because it's positive everywhere, but I'm going to put it. And then take a second and fill in the remainder. The trick I've shown you in class is that this factor of t minus 6 changes when we pass through 6. So when we go from the 2, 6 interval to the 6, infinity interval, the t minus 6 changes. It's going to go from negative to positive. That's where it switches. There's a little bit of a trick to that. The negative 2, t minus 2, will be negative, and then it switches immediately to positive. And that means the derivative is the product of those. Positive times negative gives me positive. We do the same thing for the other intervals. Since the derivative in the first interval is positive, that means the function is increasing. The derivative is then negative, which means the function is decreasing, then it's increasing. So that means that right in here, where the function goes from having a positive slope to a negative slope to a negative slope means there's a max. And right in here, where you have a negative slope changing into a positive slope, you have a min. So there's a maximum at 2, some number, and a minimum at 6, some number. And again, I don't particularly care to spend time finding those numbers. The y coordinates would be found by putting the x coordinate of the point into the original function. So if you put 2 in for t, you would get the y coordinate of the maximum. All right, let's take a look at C. This time it's a degree 4. I hope you're getting the hang of this. You're going to take the derivative and factor the result. So I'm checking my derivative here, 4x cubed minus 12x squared minus 16x. Looks good. You need to factor this. I can take a 4x out and be left with x squared minus 3x minus 4. I'll double check that, and you should be doing the same thing, but I believe it looks fine, which means my derivative is 4x times x minus 4 times x plus 1 would be the complete factored form. My critical values of x would be 0. I have a factor of 4x here. We can't ignore that. That gives me a critical value of x of 0, 4, and negative 1. I didn't mention it, but when we build our derivative table and we rewrite our domain into pieces, the pieces have to be in numerical order. We're going to go negative infinity to negative 1, then negative 1 to 0, then 0 to 4, then 4 to infinity. They have to be in order. You can't start mixing those domains up. I guess you could, but it's harder to keep track of. I'm just checking to make sure that I've got all of the critical values of x, and I think we're good. Across the top, we have a 4x, we have an x minus 4, and we have an x plus 1. 4x is negative, negative, positive, positive. I would say that the one thing you need to work on here, and you're going to have to spend some time on your own really concentrating and thinking about this, is how to complete this chart fairly quickly. I don't think it requires a lot of thought. I get negative, 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 positive. And then for the negative 1, it's negative, and then it switches to positive almost immediately. I'm just double checking my chart. The first column looks okay. The middle column looks okay. The third column looks okay. So what does that tell us about the derivative? The derivative is the product of those three things. Negative times negative times negative is positive. Negative times negative times positive is positive. My mistake here, you guys. Sorry. Negative times negative times negative is negative. The first row gives us a negative. Then positive, then negative, then positive. Which means the function is decreasing, then increasing, then decreasing, then increasing. Once you get the hang of this, it's not that difficult. We're going to have a minimum here because the function goes down and then changes direction and goes up. So we have a minimum at -1. We're going to have a maximum at 0. We're going to have a minimum at 4. And by the way, if you want to, you have graphing calculators. You could always graph this original function, not the derivative, graph the original function and confirm that those are the locations of the extreme values. Again, if you want to find the y coordinates, feel free to put those x coordinates into the original function. We have one more example left. I hope I'm not pushing it. Oh no, that was it. Well, that's good. I feel as though maybe I went too fast, but again, you can always pause the video whenever you like. On page 182, there's a number of questions in number 2 that you're going to do. Basically, everybody, they are all polynomial functions. So even though I talked about critical values where the derivative does not exist, you are not going to encounter any of those today. What you're going to be doing is finding each derivative, factoring it, and setting it equal to 0 in your mind so you can determine the critical values of x, which are where the derivative is 0, using those critical values to construct a first derivative table, completing the table to find out where the function is increasing and decreasing. And finally, if the function increases and then decreases, it has to pass through a maximum. And if the function is decreasing, so if the function goes up and then goes down, this must correspond in between to a maximum. If the function is going down and then going up, it must correspond to a minimum. I hope that was okay to follow. Have a great rest of the day. And don't forget that tomorrow, which is Friday, the Google Hangouts will be open. They're probably open right now. You could go hang out in there by yourself. There's nobody in there. But starting tomorrow, I will be in there during those times that I talked about on the first day. I think that covers it. If you have questions or you need something from me, you can email me or meet me in that Google Hangout tomorrow. Have a great rest of the day, and I hope you're successful with working on this on your own until tomorrow. Have a great night, you guys. See you later.